Today we're going to talk about reasoning about exponential graphs for the second day. So here's our starting thing. Which one doesn't belong? And we have four functions here. So we have f of n equals 8 times 2 to the n, g of n equals 2 times 8 to the n, h of n equals 8 plus 2n, and j of n equals 8 times 1/2 to the n. So keep in mind we've done these questions before. With these, each one doesn't belong for a different reason. So you would just have to think about and see what you notice with each of these. So right off the bat, which ones look different? Well, here h of n is the only non-exponential. All of these others are in the form a times b to the x power, y equals a times b to the x power. So that's the only non-exponential. This one is a line, okay? Here, if we're looking at the three exponentials, what do you notice about the a values? So this is the only, well, even looking here, this would be our y-intercept. These are the starting amounts. So the only non-y-intercept of the 0.08. Okay. Looking here, this is the only one that doubles. Oh, I'm just putting those two words together. Only one that doubles. Okay, like this would multiply by 8. This doubles it, but then adds 8. And then this one is going to take half of it each time. So all of these are increasing, so the only decreasing one. Okay, the only decreasing function. And you could also do this by looking at the graphs of them as well. So again, I have typed into the graphing calculator. Let's move this over here a little bit so you can see it. And as you're looking, so there's the 8 times 2 to the n, 2 times 8 to the n, there's 8 plus 2n, and the last one is 8 times 1/2 to the n. So you could also look at the graphs of those to see what's happening with them, okay? So there are obviously other reasons as to why these are the ones that don't belong. Those were just the reasons that we came up with here. All right, so let's keep moving on. Here we have the value of a computer, okay? And here is the graph representing an exponential function, f. The function f gives the value of a computer in dollars as the function of time x measured in years since the time of purchase. So here we've got the time in years. Time in years, okay, but that's the since the purchase, so this would be the purchase date right there. And then this is the value. So we've talked a lot about when you purchase something, as soon as you purchase it, the value immediately goes down, okay? And this one is going to go down exponentially. All right, so based on the graph, what can you say about the following? What is the purchase price of the computer? So if we're looking at this graph, we find the purchase price right here. That's the starting amount, so $400. Now, the next question asks us the value of f when x equals 1. If you look here, it doesn't count by ones, but we would need to be somewhere right in the middle here. Okay, so this would be 1, 2, 3, 4, and it would keep going from there. So with this, at 1, we would be here at 200, but let's just make sure that that actually makes sense in this situation. If it is exponential and we're going from 400 to 200, we're cutting it in half. And then after another year, it goes from 200 to 100. So if this is the 0.1, 200, we go from 200 to 100, and so it keeps cutting it in half. So that does make sense. The value there is 200. So what is that meaning of f of 1? So this is the value of the computer 1 year after purchase. Okay, this is the input value. The input is here along the x-axis. That means that it is 1 year after the computer has been purchased, what the value of it is. Okay, specifically, it's $200. All right, so let's look at a few more questions that we have going on with this. So part D says, how is the value of the computer changing in each year? Well, we just discussed that, that if it's going from 400 to 200 to 100, this point here would be 350 and then 425. So we're going, it's being cut in half each time. So now let's write an equation for that. So we would have f of, I don't know, let's just say x. It could be f of x, f of n. But it does say that it needs to be f, so we do need to use f of something here. So remember, it is an exponential. That means that we need to use our starting value, which was 400, times our factor here, which we came up with as 1/2 because each time it's getting smaller. Okay? And then that's to the x power. The last question is asking us whether the value of f will reach 0 after 10 years. So we have a couple of different ways of doing that. We just came up with an equation here. So if we plug in 10, if we actually find f of 10, so let's go here into our calculator. Again, you can use Desmos as fine as well. So we're typing this in, and it's telling us that it's a little less than 40 cents. So this would be about 40 cents. So would the value reach 0 after 10 years? The answer would be no. Okay, and remember, this means approximately. If you just put 39 cents as well, that's fine because it does round to 39 cents. Okay, so that's all using our information from that graph. All right, we got one more to look at here. Here are two graphs of two exponential functions, and for each, we want to write an equation that defines the function and find the value of the function when x equals 5. So we're going to do each of these individually. So I'm actually going to cover up this other one so that we can work on figuring out what we got going on here. Okay, so first we have to write a function. So let's say f of x equals, and we need a starting amount, and we need to know what it's multiplying by, or what our growth factor or decay factor is. So this one is growth because it is going up. So that means that our b value is going to be bigger than 1. So our starting amount, the y-intercept is 5. And what's happening here? We're going from 5 to 15 to 45 as we move along. So 5 to 15 to 45, we're multiplying by 3 each time. That means that now we're going to find f of 5 because it told us to find that. So if we plug in this information, so 5 times 3 to the 5th power would give us 1,215. So that's it for that graph. We're going to do the same thing for the second graph down here. Again, these are just applying all of our knowledge together. So since this is a different function, let's use g of x equals. Again, we need a starting amount and then our growth or decay factor. Now, I want you to pay very close attention. Even though they give us this value here, our starting amount is always going to be when the x value is 0. Okay, your starting amount when you're writing an equation is always when the x value is 0. So here, our starting amount is actually 20. Don't get confused for the fact that they gave you this over here. Okay, the reason why it has to be this, remember when we take anything to the 0 power, it's going to be 1, and when we multiply it by this value, that's going to give us our starting. Okay, so now that we have this, we got to figure out what's happening. We're going from 40 to 20. It does skip over this value of 1 here, but if we're going from 40 to 20, 20 to this y value should be 10. So 110 would be that point, and then 10 divided by 2 would be 5. So there we are, cutting it in half each time. So our b value is 1/2. And then we'll say to the x power, you could put that as a decimal of 0.5, or you could leave it as a half, doesn't matter. So then if we're trying to find what g of 5 is, so we would plug in 5 for x there. And again, we would type it in, and we get 0.625 is our answer there. Right? So it's all about starting and ending values. All right. The last thing we're going to talk about here is a good old moldy wall. So here are the graphs representing two functions and descriptions for two functions. All right, so function f is the area of a wall that is covered by mold A in square inches, doubling every month. And function g is the area of the wall that is covered by mold B in square inches that's tripling every month. So which one of those is growing faster? So since the tripling, I guess I should ask the question here. It says which graph represents each function, label the graphs accordingly and explain your reasoning. So since the mold B is growing more quickly, that means that we need the one that's going to go up at a faster rate. Okay, so out of the dashed and the solid, which one are going up at a faster rate? So this one here would be graph G, or function G, and then this dotted line here would be function F. Again, the solid line is going up more quickly, so that means that it is going faster, which would be tripling as opposed to doubling. Okay, both of them are still growing pretty rapidly. All right, question number 2 says, when the mold was first spotted and measured, was there more of mold A or mold B? And explain how we know. So if we're looking at this, we're looking at from the beginning, when it was first spotted, which of these is higher? Well, function F is, and that represents mold A. Okay, so it has a higher y-intercept. That's how we know. And then the last thing, what does this point P comma Q represent? Okay, so P is our input and Q is our output. So that means if P is our input and that's time in months, we would say after P months, there was the same amount of mold A and mold B, and that would be Q square inches. Since it's where both of those graphs intersect, that would just be a system of equations, and it's crossing at this point after P months. They share the same area of Q square inches, whatever that is. And that's it.